Hello everyone. You've spent the past couple days working on comparing two proportions, and today and tomorrow we're going to talk about comparing two means. Before we talk about comparing two means, let's review the sampling distribution for a single mean. Remember that the shape for the sampling distribution for a single mean is approximately normal if either the original distribution is normal or we have a large enough sample size, meaning 30 or more. That was the central limit theorem. We learned about that back in chapter 7. The center of the sampling distribution for a single mean is centered at the mean of the population distribution, and the spread or standard deviation of the sampling distribution depends on the sample size. We've talked about the fact that the larger the sample size, the less variation in the sampling distribution, and that's assuming that we're sampling no more than 10% of the population. So this is for working with a single mean. Now let's talk about the difference between two means. So we'd take two samples and we'd have two sample means, and we'd be looking at the differences of lots of pairs of sample means from the two different populations. Are there any similarities and are there any differences? Well, we definitely want to work with a simple random sample, and if the original two population distributions where we got our samples from is normal, then our shape of our sampling distribution of sample means is approximately normal. Otherwise, if the original distributions are skewed, we want to make sure our sample sizes for both of our two samples are greater than or equal to 30. As far as center, the center would be centered at the difference of your sample means. So the difference of the sample means is an unbiased estimator of the difference in population means. We talked about unbiased estimators also back in chapter 7. That is that it is centered at the true difference in the population means. And the standard deviation of the sampling distribution is a little bit different here. Notice, let me go back here. Notice we had the standard deviation divided by the square root of n. Now that we're working with two standard deviations, we have to combine them. We've got the sum right here, and we incorporate both sample sizes. Once again, assuming that each sample, and notice it's each sample, is no more than 10% of the population. So we'll use this formula here in a little bit. So let's take a look at this example here. It's a little bit long. We have a potato chip manufacturer. He's buying potatoes from two different suppliers. And one of the suppliers is Riderwood Farms. Their potatoes are normally distributed with a mean weight of 175 and a standard deviation of 25. That's for all of its potatoes. So that would be the population distribution. This is describing the population distribution, what I've just underlined in red. And the weights of the potatoes from the other company are normally distributed with a mean of 180, so they're a little heavier. And also they have a bit more variability. The standard deviation for that group is 30. When shipments arrive at the factory, the inspectors randomly select a sample of 20 potatoes from each shipment. So that gives you a clue that we're dealing with two means here as well, and weigh them. They're surprised when the average weight of the potatoes from Riderwoods was higher than the average weight from the sample from Camberley. And if you think about it, they probably would be a little bit surprised because the average here is 175, and that's smaller than the average of 180, the mean of 180. So, you might think they would be surprised. That would be reasonable for them to be surprised. We'll look at the probability of that result here in a minute. First, let's describe the shape, center, and spread of the sampling distribution. Well, the shape is approximately normal because we were told that both population distributions were normal. The center of the differences is going to be at 5, the difference of the two sample means. So that's the center. So the center is going to be at 5 grams, the difference of the two means. And for the standard deviation, we're going to have to use this formula back here that we saw on the previous page, where we have the standard deviation of the population divided by the square root of the sample size. So let's go down here and see what that would be. So essentially we have the variance here, because it's a standard deviation squared. That's the variance divided by the sample size plus the variance divided by the sample size. And then to actually have standard deviation, we need to take the square root. So the spread, or the standard deviation here, is 8.73 grams. So the next question here, so now let's take a look to see if they should be surprised. Normally they would expect that Camberley would weigh more than Ryder would, but this actually happened in reverse for them. It actually turned out that the sample mean in this particular sample for Ryderwood was larger than for Camberley. So if we subtract and do Camberley minus Ryderwood, since Ryderwood is actually bigger than Camberley for the means, the difference would be negative. The difference would be 0. So this is where we'd expect the difference in the sample means to be on average. There's a difference of 5 pounds on the average from sample to sample. However, what ended up happening is they got a result where if they took the mean weight of the Camberley potatoes and subtracted the mean weight of the Ryderwood potatoes, the result was negative, since the Ryderwood potatoes weighed more. So the question is, what's the probability of this happening? Well, we need to turn this into a z-score. So we take the difference in the sample means, which was less than 0, subtract the difference in the population means, which is 5, and divide it by the standard deviation of our sampling distribution. And we get a z-score here of negative 0.57. And you know that a negative 0.57 z-score is not that unusual. And so that's not all that unusual, since this would happen 28% of the time. The inspectors should not have been surprised. All right, let's take a look at an example involving confidence intervals. And then we'll look at hypothesis testing tomorrow. So basically the way a two-sample t-interval works for difference between means is we figure out the difference in the sample means. That's our statistic. Then we have our t-star value, and remember, we'll have to look this up on a table of values. The degrees of freedom normally was n minus 1, but now we're going to get the degrees of freedom by using the smaller of n minus 1 or n minus 2. So whichever sample size is smaller, that's the one we want to use. That allows us to be a bit conservative. And if you were to actually construct the confidence interval on your calculator, it'll give you a different degrees of freedom because it's using a formula that's slightly complex. It's beyond the scope of this course, and it's not something that you'd be asked to calculate. But notice that the degrees of freedom will be different, and so your confidence interval on your calculator is actually going to be a little bit narrower, because by using the smaller of n minus 1 or n minus 2, we're being a bit more conservative than what our calculator would be. Notice once again, we want to use a random sample from two independent populations or random experiment. And both populations either need to come from a normal distribution, or if the distribution is highly skewed or has outliers, we need to make sure both sample sizes are at least 30. And we also want to check that 10% condition that we've been talking about throughout when working with means. So let's take a look at this example here. I apologize for the graph not showing up well here. You have a better copy of the graph on your handout. So the question here is, do plastic bags from Target or plastic bags from Bashaw's hold more weight? A group of AP Stat students decided to investigate by filling a random sample of 5 bags. Now this is a very small sample size, so we're definitely going to have to look at these dot plots to decide if it's reasonable that the population distribution might have been normal. And to be honest, since this sample size is so small, it might be hard to tell. And that's something that we might want to be cautious about when we actually calculate and interpret our confidence interval. Because our sample size is so small, our t-star value is going to be very large because we're going to have a degree of freedom of 4. So it's something that we want to maybe be cautious about. There's quite a bit of variability here between the two bags, and notice the distributions actually do overlap. But the question is, what is the difference between the weights of the bags in terms of a confidence interval? It does look like Target holds more, but how much more? So let's take a look at this. We're going to construct and interpret a 99% confidence interval for the difference in mean capacity of plastic grocery bags from Target and Bashaw's. So yes, we have a random sample. I'm just checking the conditions here, and it was 5 for both, but there was no outliers or skewness, so we're going to say normality is reasonable, although I would use caution in this case since the sample size really was that small. And obviously it makes sense that there's more than 50 bags in the store. We haven't violated the 10% condition. So our degrees of freedom is 4, and here's our formula. Notice I'm using subscripts of T for Target and B for Bashaw's. And I know N sub T and N sub B is 5 in both cases. To get the values for the sample means and sample standard deviations, you'll need to enter the values into your graphing calculator. Enter Target in list 1, we'll say, and Bashaw's in list 2. I'm going to pause this and do that with my calculator, and you can do that with your calculator as well. So Mrs. Neville, this is where you need to pause the video for a second so the students can enter the data in their calculators. So students, this is what you should have in your calculators. In list 1, I listed the first set of data, which was for Target, and in list 2, I listed the second set of data, which was for Bashaw's. And what I'm going to do now to get the values to substitute in for the sample means and sample standard deviations is I'm going to do stat, calc, option 1 here, 1 variable statistics on list 1. So I hit second list 1, and then enter, and then go down to calculate. Oh, let's try that again. Stat, oh, I didn't change it to list 1. Stat, calc, 1 variable statistics. You guys are like, no, it needs to be list 1. There we go. Enter, enter, enter. All right, so we have our sample mean for Target of 12,843.8 grams, and the standard deviation you want to use is the sample standard deviation. Be careful of that. Do not use the population standard deviation. The sample standard deviation is a bit bigger. It has much more variability. In a sample standard deviation, in this case, quite a bit more variability than the population standard deviation since the sample size is only 5. We'll do that again for list 2, stat, calc, 1 variable statistics, list 2, go down to calculate, hit enter, and that's the sample mean, 9,234 for Bashaw's, the capacity in grams, or the weight in grams that it can hold, and the sample standard deviation is 1,474.2 grams. So we're going to substitute those numbers into the formula here. So those should look familiar. We just saw those. And this T star value, you might be wondering where we got that particular value from. I'm going to call up the T table here. So here's the T distribution from our textbook. You should have a copy of that, the yellow laminated sheet, so you can look it up there. We're doing a 90, let's see, what was it again? We are doing a 99% confidence interval. So let me go back to the table here. 99% confidence interval. That means we'd have 1% left over for the tails, and that has to be split equally between the two tails. So I'm going to be in this column. Let's just confirm that I'm in this column here. I'm going to scroll down. There should be a 0.99 or 99% at the bottom, and there is 99%. So my degrees of freedom is going to be 4. That's how I get the 4.604 number. So you should be able to find that 4.604 number on your table. So we've substituted all the numbers in the formula. We do the calculation, and our point estimate is 3,591.8 grams, plus or minus our margin of error. And when I add and subtract that value, this is what I get from my interval. Quite a wide interval, but that's not surprising because our sample size was so small. And the other reason it's so wide is we're dealing with a 99% confidence interval, and we know that wider intervals, intervals that we have more confidence in, need to be wider in order to capture the true value more often when we do this procedure. So this confidence interval right here. So we are 99% confident that the true mean difference in the mean capacity for the bags, for all bags, not just these 5 bags, but for all bags from Target and Bashaw's, is between negative 1,380 and 8,564 grams. In other words, it's possible, since 0 is in this interval, that the bags could hold on average the same amount of weight or have the same capacity.